In the lecture before the break, we started talking about maximum likelihood estimation for estimating parameters in regression models. So I'm just going to briefly review what we talked about last time and hit the major points. The first thing is that we define the likelihood function as the probability density function evaluated at the data y viewed as a function of the parameters. And then what maximum likelihood estimation does is it uses the parameters, that being the regression coefficients, and any parameters describing the variances. It uses the parameters that maximize the likelihood function. So we started with a really simple example that the response is modeled by B0 plus error, where the errors are independent and all have a normal distribution with the same variance. So this is a sort of model we've been talking about all semester long. There's a bunch of math, so this is the likelihood function, and then if you do a bunch of math to take the derivatives of the likelihood function with respect to the two parameters in this case, B0 and sigma squared, set them equal to 0, you get B0 equals the average of the data, and then sigma squared is 1 over n times the sum of squared residuals. So the point is B0 hat is the least squares estimate, and then sigma hat squares is close to what we used for an estimate of sigma squared before, except we're using 1 over n instead of 1 over n minus 1. So maximum likelihood gives you something very close to the estimates we've talked about all semester. The next example is just generalizing that to having p covariates plus an intercept. Same thing, you do a bunch of math. Turns out that the derivatives with respect to the b's give you the normal equations. And so b hat is the same estimate that we got before, x transpose x inverse x transpose y. And sigma hat squared is similar to the estimate we got before, except you divide by n. You take the residual sum of squares and divide by n instead of dividing by n minus p minus 1. And so the question we pose is that, so what's the point of maximum likelihood if it gives us estimates that are the same or maybe even a little worse than the ones we already had? I say there's a little worse because the estimate we used before for sigma squared was 1 over n minus p minus 1, and we did a lot of work to verify that that estimate that used n minus p minus 1 was unbiased for sigma squared. So if we're not using 1 over n minus p minus 1, we're using 1 over n instead, this estimate will be biased for sigma squared. So what's the point of doing all that, doing this maximum likelihood stuff, if it gives us the same or worse estimates than we had before? Well, the point is that it gives us a framework for estimates in more complicated situations. So the example we ended with in the last lecture was this one. So this is something completely different from what we've done before. The reason it's different is that we have a very simple mean, so the expected value of y is just b0, but the error term doesn't have a constant variance. The error term variance is sigma squared times xi squared, where xi is some covariate. So this is different from before because we're putting the covariate into the variance instead of the mean part of the distribution. So we can write the distribution for y as a vector, as multivariate normal. Expected value is b0 times the 1 vector. And then the covariance matrix for y is sigma, where sigma is this diagonal matrix that looks like this. So it's sigma squared, which is our parameter, multiplied by a diagonal matrix with xi squared on the diagonal. The reason it's a diagonal matrix, meaning there's zeros off the diagonal, is that we assume that these errors are independent, which implies that the covariance between any two pairs is 0. Okay, So the likelihood in this case is this formula. This is where we ended up last time. It's minus n over 2 log 2 pi. This is the log likelihood, by the way. Minus 1/2 log det sigma minus 1/2 of this quadratic form term. The determinant of sigma, since it's a diagonal matrix, we can write it as sigma to the 2n product is xi squared. And then the log, of course, would be n log sigma squared plus some log xi squared. And the inverse also has a pretty simple formula. You just take the reciprocal of sigma squared and multiply it by a diagonal matrix with the reciprocals of the xi squareds on the diagonal. Doing a little bit more math, you can see that this quadratic form term can be rewritten like this. And if you were to multiply this out, what you get is this expression. So what this is doing is you take yi minus b0, square it, divide that by xi squared, sum over I, and then divide by sigma squared. So this is the quadratic form term, and this is the log determinant term. So putting both of those things back into the likelihood, you get this expression, where this part is minus 1/2 log determinant sigma, and this part is the quadratic form. So maximizing this log likelihood function over b0 means minimizing this quantity over b0. So if you look at this expression, the only term that depends on b0 is this one. And so if you want to make the log likelihood as big as possible, since this has a minus, that means you want to make this expression as small as possible. So this is similar to minimizing the residual sum of squares, but you put more weight, meaning by weight I mean this coefficient here, on the residuals that have a smaller variance. So when xi is small, that means the residual has a small variance, and therefore 1 over xi squared is big. And so you're putting more weight on the residuals that have smaller variance. You may have heard of this technique. This is called weighted least squares, because there's a different weight associated with each squared residual. If you take so I haven't given you a formula yet for that, but this is qualitatively what you're trying to do. You're trying to minimize this expression, and that corresponds to weighted least squares. We can give a formula for the maximum likelihood estimate of sigma squared. If you take derivatives, what you get is this term depends on sigma squared. So you'll get minus n over 2 divided by sigma squared, because the derivative of the log is 1 over the thing. So that's this term. And then that doesn't depend on sigma squared, and this does. So what you get here is this part doesn't depend on sigma squared, so it's the derivative of this part times this. The derivative of this part with respect to sigma squared is 1/2 sigma to the 4th. So that's why you get 1/2 sigma to the 4th times this weighted residual sum of squares. Now if you set this expression, this derivative, equal to 0, solve for sigma squared, you get this expression. So the heuristic motivation for this expression, for why this makes sense, if you look at the variance of yi minus b0, it's xi squared, so this is epsilon I. We said that this has expectation 0, and variance xi squared sigma squared. So if you look at the variance of 1 over xi times this, you get sigma squared. And so it makes sense, if you want to get an estimate of sigma squared, you take the average of the squares of this expression. So the average of the squares of these is 1 over n times this squared. So I'm arguing that this should be a good estimate of sigma squared. And this is exactly this expression here. We didn't give a formula for B0 hat yet, and there is one, but it's actually much easier to give a general formula. So we'll do that next. In general, we might have a model with an assumption like this. So y is multivariate normal. Its expected value is x times b. So this is the same as before. And then its covariance matrix is sigma, and that covariance matrix depends on some parameter theta. So what happens is we get to observe y, and we want to estimate both b and whatever parameters are in the covariance matrix. So we'll bring this back to this specific weighted least squares example in a minute, but it's actually easier to give a general formula first and then derive what the specific formulas are. So the log likelihood function for the multivariate normal is this expression, minus n over 2 log 2 pi minus 1/2 log det sigma theta minus 1/2 this quadratic form, y minus xb transpose sigma theta inverse times y minus xb. These are all scalars, so the determinant is a scalar, the log of that is a scalar. This is a 1 by n vector, that's n by n, and this is n by 1, so the resulting multiplication is a scalar. We can take the derivative of this expression with respect to one of the b sub k's. So I've written this out with a slightly more complicated expression. So if you look at this expression, this is the only term that depends on b. This is a quadratic form, so you can write it as a double sum. And the way the double sum works is you sum from 1 to n. So the summation variables I'm using are I and L. I'm going to use, oh, there's a typo here. So this should say partial beta k, because this says partial L, partial beta k. J is going to refer to the summation over b sub j. So sum over I, sum over L, sum over j, derivative with respect to bk. This is a typo. This should see partial bk. This quadratic form, so essentially what you do is you take every possible entry of this matrix, so sigma inverse IL is taking that to mean the IL entry of sigma theta inverse. And then you multiply it by the ith entry of this vector, which is yi minus this sum, and multiply that by the lth entry of this vector, which is yl minus this thing. So this is an easier expression to work with because everything's in terms of scalars in this expression. So if we take the derivative with respect to bk in this expression, there are two terms here, so it's a sum, so the derivative of the sum is the sum of derivatives. So there are two terms here, so we use the product rule, take the derivative of the first one with respect to bk, and multiply it by the rest. So that's what you get here. So if you take the derivative of this with respect to bk, you get xik. And then you have to multiply that by this expression. So what we're doing here is this, sorry, I got that backwards. Taking the derivative of this with respect to bk, you get xlk, or minus xlk. And then you multiply it by this, and then by this. So that's this, and then this. And the second term in the product rule is you take the derivative of the expression with respect to this and multiply it by that. So the derivative of this with respect to bk is xik, multiplied by this, multiplied by this. So it turns out that these are actually the same expression. And if you add them up, you get this. So you have minus 1/2, or sorry, 1/2 and 1/2. Add them up, you get 1. And so this is what you get. So you get yi minus this times sum over L sigma theta inverse IL XLK. The k is here because we're taking the derivative with respect to bk. And if you think about this, this is actually a matrix multiplication. This part here is just sigma theta inverse times x. And then, so that's what this sum is doing. What this sum is doing is it's taking matrix multiplication of y minus xb transpose times that. So the easiest way to see this is to work backwards, to just take this expression, write it as sums, and then verify that you get back to this expression. So this is going to be a vector, and what you're getting is you're pulling out the kth element of the resulting vector. So that was the derivative with respect to bk. The derivatives with respect to any of those will just be, you pull out, instead of the kth entry, you'll be pulling out the 0th entry up to the pth entry. So if you stack all those things as a vector, you'll just get this thing as a vector. So this is x transpose sigma theta inverse y minus xb. Setting this equal to 0, you get this expression. So plug in b hat here, set it to 0. And then if you move things around, you get this expression. So on the left side, you get x transpose sigma theta inverse y. On the right-hand side, you get x transpose sigma theta inverse x b hat. So this should have a hat here. Sorry, that's a typo. And then if you solve for b hat, you'll do the inverse of this times this. So x transpose sigma theta inverse times x inverse times x transpose sigma theta inverse y. So this is what we call the generalized least squares estimate of b. We call it generalized least squares because if you were to plug in sigma theta equals to sigma squared I, which is the assumption we've been using throughout the semester so far, what this means is that I'm saying that the parameter theta is sigma squared, and the way that sigma sub theta depends on it is it's the parameter times the identity matrix. If you plug this in and work out what this expression has to be, you just get b hat equals x transpose x inverse x transpose y. So you can verify that on your own by plugging in sigma squared I here and sigma squared I here. So back to our weighted least squares problem. What happens in this problem is sigma theta is sigma squared times a diagonal matrix, where the diagonal matrix is this expression. And you remember we had a very simple form for the mean. It was just a constant mean, b0. And so if you plug in, so if you do this expression, but plug in for sigma theta sigma squared d, what you get is this. And for x, if you're plugging in 1, what you get is this. So what happens here is sigma squared comes out of here with a 1 over, because it's minus. But then it gets an additional 1 over for this, so you get a sigma squared. Sigma squared comes out of here with a 1 over, so it's a 1 over sigma squared. What's left inside of the expression will be 1 transpose d inverse times 1 inverse. And what's left here is 1 transpose d inverse y. So if you look at what's going on here, this is a quadratic form in d inverse. So this is going to be, since this is the diagonal matrix, you only have to sum over the diagonal entries. And you get this thing, and you get 1 over that, because there's an inverse there. Here, if you do d inverse times y, you're going to get a vector that's yi over xi squared. So you get a vector with these entries. And if you do 1 transpose times a vector, you just get the sum of those things. So here is the formula for b0 hat in this weighted least squares problem. So it's sort of like taking the average, but you scale the yi's by xi squared, and instead of doing 1 over n, you do sum 1 over xi squared. So you can actually show somewhat easily that the expected value of the random variable version of this is actually b0. So I'll leave that as an exercise. So in some sort of simple situations where sigma theta has a special form, you can actually figure out a formula, simple formula for what the regression coefficient estimates are for generalized least squares. Sometimes you can get simple formulas for the variance parameters. So for this problem, if we go back up, we were able to derive a formula for sigma hat squared, a relatively simple formula. But in general, if the covariance matrix depends on parameters in a complicated way, you'll need to use a numerical optimization procedure to find theta hat. And there's software out there that does that for you. What we'll do in the next set of notes is we'll explore some specific models for this, where the dependence on theta is more complicated than these examples. The next thing I want to talk about is a technique for dealing with the problem that the maximum likelihood estimates for variances can be biased by the fact that you're plugging in the least squares estimates for the regression coefficients. So that technique is called residual maximum likelihood. Often called REML. This is kind of interesting. This was discovered here at Cornell by someone named Charles Henderson, who was a statistician here. This method is sometimes called restricted maximum likelihood. I think it's actually more often called restricted maximum likelihood. So when I say residual maximum likelihood, I mean the exact same thing. I prefer the term residual, and I'll explain why below. So as I said before, the central problem with maximum likelihood is that variances get underestimated. This is because the variance estimates depend on the estimates for B, so either least squares, weighted least squares, generalized least squares. And these were chosen to minimize either the residual sum of squares or the general sum of squares. And that's why when we have simple models and we're trying to estimate a residual variance, we replace the 1 over n that we have in maximum likelihood with something like 1 over n minus p minus 1, where p is the number of covariates. So instead of this expression, which maximum likelihood gives you, we replace it with this one, which is unbiased. And the maximum likelihood estimate is biased to be too low. The problem is that for more complicated models with complicated assumptions about the covariances, and again, we're going to talk about some of those in the next lecture, it's not clear how we should adjust the estimates of the other covariance parameters. So what REML does is it offers a very clever solution to this problem. This is one of my favorite ideas in statistics. And the solution is this. We take the data vector y and we transform it to be another vector that has expectation 0 no matter what the regression coefficient b is. And then we use the transformed vector to estimate whatever variance or covariance parameter you have. So in a formula, what I mean by that is we have a vector y, so this should be a vector y. We transform it by multiplying it by a matrix M to get z. And we pick M so that no matter what b is, the expected value of z, which is equal to mxb, is equal to 0. And then to generate estimates of the covariance parameters theta, we maximize the likelihood function derived from z. Okay, so that's the general idea. We use this transform data vector where we've picked this transformation so that the expected value of z is 0. Okay, next question. How do we find such a matrix M? So basically what we need is we need a matrix M such that mx equals 0. If this is true, then if you do mx times b, which is the expected value of z, then you're going to get mx is 0 times b, which is 0, which is what we're looking for. And this will be 0, since you're doing 0 times b, it's going to be 0 no matter what b is. So it won't depend on the true value of b. And therefore won't depend on whatever estimate you plug in for the true value of b. Okay, how do we find this matrix? Well, it's actually very simple given all that you've learned in this class. We use projection matrices. So remember that capital P is the projection matrix for x. Its formula is x transpose x inverse x transpose. Implicitly, we're assuming here that x is a full rank matrix, so that x transpose x inverse exists. And then if you use m equals to I minus p and do this times x, you get x minus p times x. And since p is the projection matrix for x, p times x is just x, and so you get x minus x equals 0. So we set m equal to I minus p. So if you plug that back into this expression here, we're using z equals m times y. You get z equals I minus p times y, and so you have y minus py is equal to z. And remember that when we got the fitted values for y, that was equal to p times y. So p times y is the fitted values. And so z is equal to y minus the fitted values, which is exactly what we've been calling the residual. So like yi minus yi hat. So this is why I like to use the term residual maximum likelihood, because you're doing maximum likelihood for the residuals for regressing y on x. Okay, so now the assumption was that the vector y is multivariate normal, expected value x beta, covariance matrix sigma theta. Since z is equal to m times y, that means that the distribution of z is normal m times expected value of y, so mxb. We picked m so that mx is 0, so z, this expression will be 0. And the covariance matrix is just m sigma times m transpose. So this is just the formula we're using to get the expected value and covariance matrix for a linear transformation of a vector. Okay, so z is multivariate normal. That means we know what its likelihood function is. It's minus n over 2 log 2 pi minus 1/2 log determinant of the covariance matrix for z, which is m times sigma times m transpose, minus z transpose times m covariance matrix for z inverse times z. So z is a n by 1 vector here. The reason we're not subtracting off anything from z here is because we would be subtracting off 0. And so the idea for REML is we maximize this residual likelihood, so I'm writing RL, over theta to get theta hat. And if you'll see here, now this expression doesn't depend at all on what b is, the regression coefficients. Okay. Now there is one problem. The problem is that I minus p, which is n, is not full rank. What I mean by that is, so this is a n by n matrix. Its rank is something less than n, and its rank is n minus p plus 1, where p plus 1 is the number of columns in X. What this means is that no matter what y is, some elements of z are exactly recoverable given knowledge of the other elements. That's kind of slightly difficult to understand, so let me try to explain this a different way. It means that the distribution of z is degenerate. In other words, the distribution of z is concentrated on an n minus p plus 1 dimensional subspace of Rn. So it has to live in this subspace, which means that the likelihood becomes infinite. If that's too much to handle, which is kind of a weird thing to think about, there's really simple explanation with the formula for the likelihood function. So one of the terms in this likelihood function is the log determinant of m sigma m transpose. The determinant of a product of matrices is the product of the determinants. So if you take the log, you'll get 2 log det m's for this one, and you'll get a log det sigma theta. M, which is I minus P, is not a full rank matrix. So that means it's a singular matrix, which means its determinant is 0. And so the log of 0 is minus infinity. So that's a problem. The other problem is that this product is an n by n matrix, but its rank is less than n. So therefore it's singular and its inverse doesn't exist. So we can't evaluate this expression either. So inverse doesn't exist, and this is minus infinity. So that's a problem. So the solution to this problem is to replace m, which is I minus p, by any n minus p plus 1 linearly independent rows of m. So m is an n by n matrix, which equal to I minus p. We're going to replace m by a matrix m tilde, and the way we get m tilde is we start taking out rows until we're left with n minus p plus 1 linearly independent rows. So this thing is no longer a square matrix. It's wider than it is tall. And then instead of using z equals my, we use z tilde equals m tilde y. So the size of z is n minus p plus 1 by 1. And we use the likelihood for z tilde to estimate theta. And that likelihood is this expression. So m tilde sigma theta m tilde transpose log det of that minus this thing. And here z tilde again is m tilde times y. The kind of cool thing about this is it turns out that it actually doesn't matter which n minus p plus 1 rows that you pick, these linearly independent rows of m, as long as they're linearly independent. So as long as you pick n minus p plus 1 linearly independent rows, you'll get the same maximizer, or the same likelihood function for theta. So then after you get theta, you plug in the estimate, theta hat, and use the generalized least squares formula to get the estimate of b hat. So one way to think about REML is it forms the residuals, gets an estimate of theta first. Theta describes the covariance parameters. And then you plug that in to generalized least squares and get an estimate of b hat. The method for maximum likelihood usually goes in the opposite way. the estimate of, you get an estimate of b hat, and then you plug that in and get an estimate of sigma squared, or whatever parameters you have in the covariance matrix.